Okay, so we're starting with problem number 17. We're being asked to graph an exponential function, and so doing this is really just using a table of values. So I'm going to just create an XY table, okay, and we're going to just pick some numbers. So we're going to pick just -2, -1, 0, 1, and 2. Those are good values, right? And before we even get into that, we're going to actually answer 18, 19. Okay, and 20, which are hiding down here, because they're going to help us to make sure that the graph that we're drawing in 17 makes a lot of sense. Okay, so when we're talking about the range, let me remind you that the parent function, which for this one is just 2 to the x, right? If I get rid of multiplying by -2 and adding 4, those operations, 2 to the x is left over. That is roughly going to look like y-intercept of 1, okay? And then there's going to be an asymptote, so let me get my pen tool, my drawing line tool, right? So we're going to have an asymptote right on the axis, okay? So it's going to look like right here, right? There's going to be a wall, which we call an asymptote, and the graph will not go below that. So again, we're not graphing problem number 17 right now. We're just kind of trying to remember what the parent function looks like. And here's going to be a rough sketch. We're going to say it's going to shoot up on the one side. It's going to go up really fast, okay? And then on the other side, it's going to start approaching that asymptote, that wall, and it's going to get closer and closer and closer, and it's going to ride right along it, but it will never actually go over it. Okay, so this, if I were to describe the parent function, I'm going to say it looks like the range is y is greater than 0, and I would describe this asymptote, this dotted line, as y is equal to 0. Right? So the very first thing to remember is that there's a connection in exponentials between the range and the asymptote. They use the same value. Right? So all we're doing in this problem, when I put that +4 on the end, is I'm going to make it so that the asymptote goes up by 4, and all the other points follow right along. So this is going to go up. Ooh, let me grab the middle of it. This is going to go up here, and so the wall is actually going to be up here now, right? So it's not going to pass the green line here. And we also have a -2, and so instead of it being above the line like this, it's going to be below the line and it's going to come down. So we can kind of get a picture in our head before we ever actually draw this graph about what it should look like. So what we're expecting when we plug in these values is to kind of get a graph that rides right below the asymptote that's up at 4 and then goes down, and I know that because of the reflection from my a value. Right? So let's fill in the information here. Because I had this +4, I know that my asymptote moved up to y equals 4, and I know that my graph is going to go as high as 4 and then go down. So we're going to use y is less than 4. Right? So you can see what the d value and the a value have done to my original parent function. They moved it, the range up to 4, and then they also sent it going from being greater than to being less than. Right? So we have two things to consider. So let's clear this out and let's graph our regular one. We kind of know what it looks like. I'm going to leave the asymptote there because we know it's going to be there, so we might as well keep it. I'm going to start plugging in values. So when I plug in, let's plug in some simple ones. When I plug in the 0, right, this is going to say -2 times 2 to the 0 plus 4. And be careful that you do your order of operations. Order of operations says simplify this exponential first. So 2 to the 0 is just 1. So this really says -2 times 1 plus 4. Then I got to multiply, so this can just be -2 plus 4. And then it looks like when I add those together, I get 2. Right? So when I plugged in 0, I got back at 2. Right? And so I'm going to let you go through and do this on your do this by yourself. When I plug in a 1, okay, I'm going to get -4 plus 4, which is 0. Okay? When I plug in 2, it's going to be 2 squared, which is 4, times -2. 4 times -2 is -8. -8 plus 4 is -4. Okay? And then on the other side, here's where we have to start thinking about what do negative exponents do. Right? So I'm going to show you one of these. If I do 2 to the -1, it's going to look like -2 times 2 to the -1 plus 4. Negative does reciprocals, right? So I'm going to say this, instead of this being 2 to the -1, it's the same as 1 over 2 to the first power. This is being multiplied by -2, and then we're going to add 4 last. Well, -2 times 1/2, that's what 1 over 2 to the first power means, is 1/2. When this is just -1 plus 4, okay, and that looks like 3. Okay, and when I plug in 4, it's going to be -2 times 1 over 2. I'm sorry, when I plug in -2, it's going to be -2 times 1 over 2 squared plus 4. So this is going to be 1/2, right? Or -1/2, -2 times 1/4, right? So -1/2 plus 4, which I would call we'll just call it 3.5, right? Something like that. That's about what's going to come out there, right? So you can see that my values are getting really small. They're getting negative really fast, but when I try to get close to 4, I'm kind of slowly creeping my way there, and we're never going to get there. And that's what we expected because of this dotted line, right? Remember the asymptote. It should approach 4, but never actually get there. So we went from 3 to 3.5 because it couldn't get much closer to it than that. So let's graph these and see what happens. -2. Well, we already know what happens, but let's graph it and actually see it happen. Right? -2 goes up to -3.5. -1 goes to -3. 0 goes to 2. 1 goes to 0. And 2 goes down to -4, which is right here, right? And so we can kind of start seeing the shape of that graph. We know that on the left-hand side, it's going to approach the asymptote and ride right along the line, okay? And then it's going to curve, and it's going to turn really sharply and head pretty straight down, not exactly, right? It'll look something like that, right? So you can see everything that we predicted by answering the questions about the range and the asymptote and the y-intercept, which for us we saw when I plugged in a 0. I got back a 2, right? We graphed that. We did that one. Y-intercept is plug in a 0. Tell me what comes out, right? So you can see that this is the graph that we predicted. It's a good representation based on looking at the function, comparing it to the parent function, and kind of predicting what's going to happen, okay? So let's talk about some of these word problems dealing with compound interest and exponential growth and decay. So for this problem, we're going to highlight some key information. Right, I'm going to start off and say, okay, I see $9,000 investment. That's my starting value. I see compounded, which means I need to use the compound interest formula. I see quarterly, which is going to be the end value for that compound interest formula. I see my percentage. That's going to be R, okay? And I see the number of years, right? So there's the information that I need. So let's kind of write down the formula so we know what we're plugging in. The compound interest formula looked like P times 1 plus R over N to the NT, okay? And I just found all of the information, right? This is P. This is N, right? 4 in this case because of quarterly. This is T, okay? Let me fix something real quick. I said NT, but then I wrote N over T. This is supposed to be NT. Sorry about that. Right, and then this value right here is R. But remember, R needs to be in decimal form, so I'm going to say 0.0725. So now it's really just a matter of plugging in and simplifying. So I'm going to say this is really going to be 9,000 times 1 plus 0.0725 over 4 to the 4 times 6. Okay, so let's simplify just the inside of this, and we'll also simplify the exponent. So it's going to be 0.0725. Okay, let me fix that. 0.0725. I did 0.725. 0.0725 divided by 4, and then I'm going to add 1 to that. Okay, so it looks like it's going to be 9,000 times 1.018125 to the 24th power. Right, so again, now we have to do the exponential first, so make sure you raise that number to the 24th first, multiply by 9,000, and it looks like we're going to end up with $13,850.61. That would be our final answer for that one. Okay. Problem number 2 is also using compounding, except if you notice in this case, they're telling us what's going to come out of the function. They're saying you're going to have $5,000 when you're done. What did you need to start with, which means we don't know what P is. So I'm going to say this is P times, and I know the rest of it. I know it's going to be 1 plus, here's my R, 0.03. And then N in this case, it says compounded daily. Daily would be 365 times in a year. And I'm going to say that this is 365 again, that same N value, and they told us about 6 years. Okay, but I know when I multiply all this out and simplify it that I'm going to get 5,000 when I'm done. And so they're wondering, what does the investment have to be so that I will have $5,000? So again, I can simplify this entire B value, we call it, right, and then I can raise it to this exponent and turn it into a number. So let's do that. Right, so I'm going to say 0.03 divided by 365, really small number. Okay. Add 1 to that, okay, and I get this really, really tiny number, and then I'm going to raise that to the 365th times 6 power. Ooh, let me clear that out. Okay, clear entry. I'm going to do 365 times 5, okay, and I'm going to get 1,825. So I'm going to raise that really small number, 1.00008 about, right, to the 1825th power, and I'm going to get a number about, right, p times, it's about 1.1618, right? We want to keep some decimal places, okay? So when I simplified this entire expression, raised it to the 1825th power, I got about 1.1618. So if I want to know what p is, I'm going to do divide both sides by this, okay? And that's going to leave p alone, okay? 1.1, let me fix that, 1.1618, right? And I'm going to do 5,000 divided by that. On my calculator, not on the screen, 5,000 divided by 1.1618 is about $4,303, right? So depending on how you rounded, if you didn't round as much as I did, or if you just use the value on your calculator, yours might be a little bit different, okay? So this is about 67 cents, right? So you'll be off by a couple dollars here or there, depending on how much you rounded, okay? So here are our last couple of problems. So the first one is talking about population growth, right? So we're going to say, again, let's look for our key information. I see currently 10,000 Sims in my Sims community. There's my rate, 0.0325, okay? And here's where it's important about this one. They're saying 3.25% is happening every 7 years. So we're only going to apply that increase on every 7th year. So when they're talking about 70 years, we're not going to plug in 70 for the value. We're going to plug in only 10 for the value, because 10 increases are going to happen in 70 years. Okay, so here's what the big thing I want you to point out about this problem is there's no word compound in this problem, which means we're going to use the simple exponential growth formula, which was a times 1 plus r to the t. Okay, and t in this case represents the number of increases, not the number of years. So be careful. So we're just going to type in, or write down, 10,000 times 1 plus, there's my r value, 0.0325 in decimal form. And again, t is not 70, it's not the number of years, it is the number of increases that have happened in 70 years, which we know in this case is 10, right? So I'm going to just, again, simplify. We're going to say, okay, come over to my calculator again, let it do its magic. 1 plus 0.0325 is just 1.0325, right? And I'm going to raise that to the 10th power first. And again, I get a nice big number. It's a nice long number. It's, in this case, about 1.377. And I'm going to multiply that by 10,000, which is our starting value. And we're going to say that after 70 years that there are going to be 13,769 Sims in my Sims community. Right? We're talking about a real life thing, so we're going to round to the nearest whole Sim. We're not going to keep any decimal fraction parts of Sims. Okay, the last problem. Given the function j of x is equal to, and then they give us our expression 5,000 times 1.625 to the x, they want us to identify the percent increase. So really what they want to know is, what is the rate? So this problem, this expression, is really like one of our rate problems right here. So this 1.625, right, that's where the rate was. Remember this number right here, okay, we plugged in a percent. They want to know the percent. So really what I'm saying here is that 1.625 is the 1 plus r from our formula. So if I want to know what r is, which is the percent, I'm just going to subtract 1 on both sides, and I'm going to get 0.625. That's the rate. That is the percent increase that they asked about. But I'm going to put it in percent form for them, and I'm going to move the decimal place 2 times to the right to do that. If I move the decimal point once and twice, I get 62.5%. And that would be the percent increase. Okay, we can do the same thing with if they talk about percent decay or percent decline or any other thing like that. Just put a minus sign here instead of a plus sign, and that will accomplish the same goal.